Okay, can everybody see the pad, the whiteboard?
Yeah.
Okay, so how about the transition?
Yeah, that looks good.
Okay, great. Yeah, this time it works well. All right, so let's start. So I would appreciate that if you have already started doing homework for, although the workload is not heavy, but still need you to take time to at least to understand how the formulation about SVMs, how we uh, get to the deal solution, right? And how does deal solution, what kind of insights does deal solution reflect, right? What are support vectors, all kind of stuffs. So please do it right now rather than just uh, until like 3 hours left, right? So let us continue with our discussion last lecture. Right today, we're gonna finish up everything about support back machines. Right. So in the last lecture, we have uh, discussed about how to get the results by solving the dual form of SVM. Right. So it turns out that we can simplify the dual form to be a quadratic minimization problem with respect to the Lagrange multipliers, right? One type Lagrange multipliers, alpha i's, which correspond to the constraints regarding the functional margins, right? So if we write down the simplified objective, right, it forms is like that. So you're going through training example twice, right? Training set twice is a double summation, right? I and j, and then the summon will be alpha I times alpha j times yi times yj, the inner product between xi and xg, right? And then subtracted by the summation over all the multipliers alpha i's, right? And of course, you need to put some constraints where for every alpha I, you have the box constraint, which it is between 0 and c, and also you have a summation constraint that alpha I yi equals to 0, right? Of course, it applies to every, um, oh, sorry, um, it applies, uh, it applies to um, every alpha I, right? So, so this is a typical quadratic convex optimization problem. You can apply any standard mature package to solve that, right? And then we talk about when we get the solution, right? So we write the optimal values of all those alpha j by alpha j stars, right? How do we recover the optimal w and optimal b, right? So optimal w is pretty easy, right? When we simplify the dual form, remember the dual form, arranged dual form is a max mean optimization problem, right? When we simplify the inner minimization problem, we take the gradient, set gradient to 0. We have already obtained that the optimal weight vector is a linear combination of all the training inputs, right? And weighted by the alpha j, right? And yj and xj, right? So this is actually very important insight, right? And later we'll review what do support vectors mean, right? But to recover B star, it's not that easy, right? We need to utilize some uh, basic results from optimization theories called KKT condition, right? And you utilize the complementary slackness from KKT and also use your zero gradient result. You can finally infer B, right? So I'm not gonna I'm gonna skip those details, but I encourage everybody to follow the logic chains and also the algebraic operations to derive everything. It's really elegant. It's really important. Um, and uh, and finally, right, from the result here, right, we can represent the final weight vector by a weighted combination of the training inputs, right? What we found is that actually most optimal RFGs are simply zero. That means most of those training examples do not really determine our final weak vector. Right? Final weak vector only determined by a small subset of training examples whose alpha j star is strictly bigger than 0, right? So we call this set of training example as support vectors. Right? So we denote it by S, means they correspond to the training examples whose optimal alpha j star strictly strictly bigger than 0, right? So and an interesting analysis shows that support vectors can only stay on the margin or inside margin. So they are essential outliers. Right? That's very interesting. Right? So we know that the idea of the soft SVM, right? We want to find the majority of training examples that are linearly separable. Right? We want to find linear classifier for those separable data points with largest margin. Right? At the same time, we allow as few examples as possible to break into the margin. Right? So if this is your classification hyperplane, right? We believe that most training examples is gonna be well separated by this hyperplane outside the margin, right? But they won't determine the position and angle of the hyperplane. The position and angle of hyperplane are only determined by those examples who can stay on the margin or intrude the margin, right? That's that's the interesting fact we can observe from SVM learning. Right? So that's a brief review about SVM dual form. Right? Again, I highly encourage everybody to follow all the logic. It's not hard. It's just kind of mechanical. It's practice of our calculus and linear algebra. But the results and the insight reflected really interesting. Okay. And then we talk about how do we, based on the dual solution, right? The structure of the dual solution to extend our linear classifiers to nonlinear case. So the idea, we have discussed about this idea before, right? So it's very naive, very straightforward. That is, if in the original feature space, we're not able to find a separating hyperplane, give a good accuracy, how can we do that? We do some high dimensional feature mapping, right? So suppose the original feature space is 2-dimensional. So now I can come out a nonlinear feature mapping to map them into a higher dimensional space. So x1 tilde, x2 tilde to xn tilde, right? N can be much, much larger than 2. Right? And we expect that in a much higher dimensional space, nonlinear dimensional feature space, we can find a separating hyperplane, which can give a much better prediction accuracy. Right? That's the key idea. Right? So we found that actually, if we want to perform some feature mapping and then learn a linear classifier in a mapped feature space, it's very convenient to implement in our dual form, right? In a dual form of SVM. How? Right? So first, from the learning objective, right, we see that we have reduced our objective in a dual form as a quadratic minimization problem, right? So if we perform a feature mapping before, right, we can just replace in the objective this inner product in the original space by inner product after feature mapping, right? Meaning that we just replace xi transpose xj by phi xi transpose phi xj, right? That's it. And all the other optimization exactly the same, right? Why? Because we're trying to optimize alpha I and alpha j's, right? So this inner product itself is constant to, it's just another constant coefficient to this alpha I, alpha j, right? It doesn't matter, right? It doesn't change any like optimization behaviors. I mean, the algorithm steps. Right? And if we look at the prediction step, right? So we know that the prediction, so let me write down with the red color again, right? When we do the prediction, our prediction rule is take the sign of prediction score, right? So you're gonna perform W transpose phi x X is test input in original feature space, right? I need to first do a feature mapping, and then calculate this linear function, and then take the sign, right? So from the structure of the dual form, right, we know that the optimal weight vector is essentially a linear combination of the support vectors, right? We just replace this, replace W by this, right? So we can get that our prediction rule is a sign of a summation going through the support vectors, where W is replaced by this, right? By this weighted summation. So it is just alpha I star and yi corresponds to the label of the support vector, and then phi xi transpose phi x and plus b, right? So you can see that if we do not perform feature mapping, this part is simply xi transpose x, right? But after you perform feature mapping, you learn the linear classifier in the higher dimensional feature space. You just replace the inner product by the inner product of the mapped feature vectors, right? So the operation is you just add one more operation, right? So conceptually, it's really easy, right? There's no need to build up new hypothesis spaces and new learning algorithm. Everything stays the same. But what is the
constraint on phi, like the type of feature transformations that we can do, or can it be any type of feature transformation?
Yeah, it can be any type of feature transformation, and it's totally defined by the user. Okay.
Yeah.
Okay. So, but here, what is the problem here, right? So the problem from the dual form structure, whatever things we have discussed so far, looks like it is pretty easy, right? We do not need to change our linear classifier structure. We do not need to change the optimization procedure, right? And we do not need to change the prediction procedure, right? And what is the problem? The problem mainly lies in the computation. Why? Because numerous practical experience tells us that if you really want to uh, enhance or boost the performance, right, you have to make this phi to be very complex, to be very high dimensional. Like it's very common that your original feature space might be like 100, and you need to construct a 1 million dimensional feature space to ensure you get good performance. And there is an even more ambitious mapping that phi gives an infinite feature mapping, meaning that, okay, I can map a two-dimensional feature vector to an infinite dimensional feature space. In that way, if you want to explicitly compute the feature mapping between, say, the support vector and test input, then in a mapped feature space to calculate dot product, it is practically infeasible because you will never be able to explicitly compute an infinite dimensional feature vector, right? Then how do we address this computation problem, right? How do we get over it? That's the thing we discussed at the end of last lecture, right? That is about kernel trick. So basically, we can imagine that for any input X and Z in our original feature space, right? So of course, we can explicitly perform some feature mapping through our predefined phi, right? And then calculate the inner product. Right? This is essentially a function, right? It's function of X and Z, right? And to calculate the value of this function, right now, we can what we can do is just direct computation, right? Naive computation. We perform feature mapping, and in a mapped feature space, we calculate inner product, which is really expensive in practice, right? So naturally, there comes a question, right? Can we compute it in another way, such that I only need to compute this function in the original feature space? but the result is exactly the same as the explicit feature mapping and then the dot product. If we can find the way to compute the function, then this function is called kernel function, and this trick is called kernel trick. That's the whole idea. That's the key idea. But you might think it's still kind of like abstracting, right? We still haven't saying why is this effective or important, right? So next we're gonna talk about some detailed example through which we can say the power of kernel trick, right? So by here I just want to summarize the kernel trick again, right? So as we just said, right, we can view explicit feature mapping and then dot product as a function over the original two inputs, right? So it's a bivariate function, right? So in both training objective and the prediction, we need to calculate those functions value, right? But if every time we need to do the explicit feature mapping and then in the product, it will be very expensive, we gain nothing, right? So kernel trick is that if we can compute the value of k without explicitly writing the blow up representation and then dot product, then we can gain a big computational advantage, right? This is the idea, right? So now let us look at example, right? We briefly talked about that at the end of last lecture, right? We're gonna give a more detail about that example to showcase the power of kernel trick, right? So suppose we want to perform a feature mapping, which is just a quadratic. What does it mean for quadratic, right? In general, our original feature vector is assumed to be n-dimensional, right? We just want to enumerate all possible ordered from 0 to 2 across these n features, and so that we can get a much longer feature vector, right? Mapped feature vector, right? How can we do that? Is actually the mapped feature vector consists of three parts, right? First, all degree 0 terms, you know, is just 1, right? And all degree 1 terms, they are just the original features, x1 to xn. And then all degree 2 terms, right? We just enumerate every distinct pair of the features, multiply them together, right? So we know that it could be x1 squared, x2 squared, xn, s2 xn squared, then x1, x2, x1, x3, x1, x4, x2, x3, blah, 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 until xn minus 1 xn, right? So we can just count how many features after the feature mapping, right? So no, there are only one degree 0 term, right? And degree 1 term, which are just the duplicate or a copy of the original features. But for degree 2 terms, we know that there can be O(n) squared, right? So essentially it is n times n plus 1 over 2, right? So if we add them together, you'll see, okay, the dimension after feature mapping, which is like O(n) squared dimension, right? But the original feature space, your feature vector is n-dimensional. So imagine if your n is simply 1000, then after feature mapping, your dimension is about like 10 to the power of 6, which is 1 million, right? It's very high dimensional, right? So you can imagine that, okay, if I want to compute it explicitly, right, of the about the inner product, right, I'm gonna first map them to the 1 million dimensional vector, and then calculate the inner product of two 1 million dimensional vectors. That's very expensive, right? So we just, for convenience, we just denote this explicit computation by A, right? Suppose I want to compute A by first perform feature mapping over X and Z, and then calculate inner product in a mapped feature space. And now we know that it will take time, complexity, like O(n) squared. Why? Because you need to first construct a mapped feature vector, which takes O(n) squared, right? And for two vectors, take O(n) squared, and then inner product between these two n squared, almost n squared dimensional feature vectors, and the time complexity will also be O squared. You add them together, it's still like O squared, right? So now we want to show that actually you do not need to explicitly compute A, right? And we can compute another quantity, right? Which is purely in the original feature space. But the result is equivalent to A. So here is how we compute B, right? So B is to first calculate the inner product between X and Z, which are in the original feature space, right? And adds 1 and take square. So now we'll show that, okay, the two results are equivalent. Only differs in coefficients, but the coefficients do not really matter because if we just skew some mapped feature, and we can make the results exactly the same. Okay, any questions so far regarding the setting before we manually check the results? Okay, great. So now let us check, right? So for convenience, we just assume, okay, original feature space is just two-dimensional, right? So we have two features, right, x1, x2, and when we map them to the quadratic feature space, this is degree 1 term 1, right, and degree 2 term, degree 0 term 1, degree 1 term x1, x2, and degree 3 terms x1 square, x2 square, and x1, x2, right? So we see that they're in total like 6-dimensional, right? So for convenience, right, so I'm gonna write down phi z, right? Z, by the way, I mean write it clearly. Z is z1, z2, right? And x is x1, x2, right? So phi z will be, I just replace x by z, right? Z1, z1, z2, this degree 1 terms, and degree 2 terms will z1 square, z2 square, and the z1, z2, right? So now let us just manually calculate A, right? So we have two feature mappings here, right? And then when we compute their inner product, we just multiply the elements in pair and add them together, right? 1 multiply with 1, you get 1, x1, z1, you get x1, z1, x2, z2, you got x2, z2, and just do it, right? x1 square, z1 square, x2 square, z2 square, and x1, x2, z1, z2, right? Let me check if I missed anything. Yeah, that's right. That's correct, right? So now let us check the result of B, right? So we know that when we calculate B, we never perform any feature mapping, right? We just calculate a function of x and z in their original feature space. So B equals to 1 plus x transpose z, right? We just look at here, right? Their inner product is simply x1, z1 plus x2, z2, then take square, right? So the remaining thing is quite mechanical. Just expand this square of summation, right? So when we expand the square of summation, we know that the two types of terms, right? We take the square of each individual elements in the summation, and then we add up all the cross terms and multiply by a coefficient 2, right? So first take the square of the 3 individual terms in the summation, right? Which will be 1 plus x1 z1 square, right? And x2 z2 square. So I'm gonna write down the power 2 individually, right? And then cross terms, right? We actually have 3 cross terms, and we need to multiply 2 because they're gonna appear twice, right? So this one and this one, we have 2 x1 z1, right? And this one, we have 2 x2 z2. And this one and this one, and 2 x1 x2 z1 z2, right? So this is the result of calculating B, right? Now let us contrast the two results, one from A, one from B. And let's just first ignore the coefficients, right? And say if their items are kind of corresponding to each other, right? So first, for the constant one, right? Both A and B have here, right? And then for x1, z1, right? We have x1, z1 here. We have x1, z1 here. The difference is okay, in B, we have a factor 2, right? And x2, z2, x2, z2, right? And x1 squared, z1 squared, right? Here. x2 squared, z2 squared, here. And finally, the product of the four, right? x1, x2, z1, z2, we got x2, x1, x2, z1, z2. You see that actually all the items contained in A also show up in B, right? In other words, they're equivalent in some sense. Right? Someone may worry about the coefficient here, right? Actually, if we can skew the mapped feature in phi, actually they can be exactly the same. Like if you want A to be exactly the same as B, right? How do we change phi, right? We can just put the second mapped feature, a factor, square root 2, right? And third mapped feature, square root 2, a factor, right? And the last feature, square root 2. Right? So then your mapped feature vector for Z will be also here, square root 2 here, square root 2 here, square root 2 here. And now if we calculate A again, right, it will have exact match even in the coefficients. That's why we say, okay, the coefficients doesn't really doesn't matter, right? So what can we say from comparing the computation results for A and B, right? We do this manually. What kind of things can we reflect, right? So you can see that both computation yield the same results, right? But the complexity are totally different, right? If you compute A, right, you first perform feature mapping and then calculate the inner product, right? As we analyzed before, the time square will be the time complexity will be O n squared. Right? But how about the time complexity to compute B?
On.
Yeah, O n, right? Why? Because when you calculate inner product between x and z, you're in an original feature space where every vector is n-dimensional, right? Your inner product takes O n complexity, and then you add a number and take square O constant, right? So you compute the computation of B is just O n, right? But the results are the same, right? Or maybe in the two-dimensional space, you didn't see the power, right? But as we mentioned, as we gave the example just a minute ago, right? What if n equals to 1,000, right? And if you naively compute the mapped feature vectors dot product like A, you're gonna take a complexity of 1 million, right? But if you use B to compute, right, your time complexity is proportional to the dimension of the original features. Right? This is a huge reduction. Right? So in this way, we can dramatically reduce the time complexity, right? When we extend our linear classifier to nonlinear classifiers. Any questions so far? In some case, like you have to use kernel trick. Why? Because phi is infinite dimensional. Later we'll say one example, one famous example. It is used everywhere in a kernel learning, kernel SVM, all kinds of kernel method. But the corresponding feature mapping is infinite dimensional, meaning that you cannot explicitly compute it. In that way, you have no other choice. You have to use the kernel trick. Okay. So here I want to summarize kernel trick here, right? So kernel trick is a computational trick which can save the time and space by computing the value of this kxz by performing operations in the original feature space rather than explicit conducting feature mapping in a product without feature transformation here. This is a kernel trick. Here is just the analysis of the computational efficiency, right? Which one I have done. Okay. So any question regarding the understanding of the kernel trick, or any other thought or question regarding the idea of kernel trick?
Yeah. So for the kernel trick, right, we've seen an example for quadratic, and like I definitely see how that's working. How do we expand that to like non-quadratic, right? Like cubic or other kinds of feature space expansion. And you said like infinite feature spaces as well, where we have to use the kernel trick. What does that look like?
Yeah, that's something I'm gonna discuss right now.
Cool.
Yeah. Okay. Any other question? I mean, just in understanding concept of kernel trick. We're gonna look at some details right now.
Just one other clarification with that. So what you just showed for the kernel trick was only in relation that equation for B is only in the case where you have for the quadratic kernel. Okay.
Yes, exactly.
So basically,
yeah, basically, what it said is I know that. So basically, we want to find some. This is called kernel function, which corresponds to the calculation of the kernel function is highly efficient, but the result corresponds to some explicit feature mapping and inner product.
Right.
But this relation is not like bidirectional. Not only, I mean, it does not guarantee every feature mapping you're gonna find an easy to calculate kernel function.
Right. Okay.
It does not guarantee, but in a valid family of kernel functions and through all kinds of assembly combination, you can construct a lot of very complex kernel functions which corresponds to highly expressive feature mapping.
Okay.
So cool. To save the computation, we usually just restrict ours to valid kernel functions.
Sure. Okay, that makes sense.
Okay. So now let us talk about the properties of kernel, right? So a natural question will be, okay, looks like as long as we can compute a function of a bivariate function k, x, and z, we can make it equal to some feature mapping, and then in the product, and the answer is no. So we cannot ensure every function is a valid kernel function. So what is a valid kernel function? It must be equivalent to an inner product after some feature mapping. This is definition, right? So that does not mean like every bivariate function is a valid kernel function. It's actually only a very small subset of functions in the whole bivariate space of bivariate functions are valid kernel functions. And then a natural question, right? Now, suppose we are given an arbitrary, let me write denoted by k theta, right? Arbitrary bivariate function k theta x and z, right? How can I justify or how can I verify this is a valid kernel function? One way is to just to form the definition. I want to find out a particular feature mapping phi, right? And like let me denote it by phi theta, right? If we can show that, okay, for this particular k theta and for arbitrary x and z, it is equivalent to first performing the feature mapping phi theta over x and z, and then do the dot product. Well, that's fine, right? But this is not this is not always easy, right? Actually, in most cases, it's not easy. And a more commonly used method is to construct the so-called Gram matrix and show that for arbitrary Gram matrix, if it is always positive semi-definite. this checking condition is also called a Mercer's condition or Mercer's theorem. Okay, so before we reach to Mercer's condition, right? Let us first review what is the definition for positive semi-definite, right? So I believe everybody has heard that concept before, linear algebra course, right? We just do a review, right? So we say a symmetric matrix M is positive semi-definite if for any non-zero vector Z, we have this quadratic non-negative. Right? So Z transpose MZ is a scalar. So that's where we should say it is non-negative. It's not vector. It's not matrix. It's a scalar. Right. So this positive semi-definite has a strong connection with the property of the matrix itself. Like we know that if a matrix is positive semi-definite, then all of its eigenvalues are non-negative, right? And the positive semi-definite matrices, some definitions are useful properties to characterize many interesting mathematical objectives. So if in the future you want to do more machine learning or optimization or all kinds of other steps, you see, okay, positive semi-definites are nearly appears all everywhere. Okay, so now let us talk about like grand matrix and kernel matrix. Right? So what is grand matrix? So grand matrix is computed based on a finite set of input vectors. Like suppose the number of those finite set is n, right? So the result of the grand matrix is n by n, right? So we denote by G. Each element in this J is just the inner product of the corresponding vectors. Say the ith row and the jth column, their intersect, right? G is computed by the inner product between xi and xj. So you can imagine this is a n by n matrix, right? So the first element will be x1 transpose x1. The second element along the first row will be x1 transpose xj, x2, right? And you continue x1 transpose xn, right? And the first row, the first element will be the second row. The first element will x2 transpose x1, x2 transpose x2, until x2 transpose xn, right? And you can write down everything here. It will be xn transpose x1 until xn transpose xn. Right? So this is called grand matrix. And of course, we can also compute grand matrix after feature mapping. Right? So say your original input vectors x1, xn, right? We first perform some feature mapping, no matter it is finite dimensional, infinite dimensional. Right? We can write down the mapped feature vectors by phi x1, phi xn, and then we can construct grand matrix. Right? So an interesting property of grand matrix is that it is always positive semi-definite. Why?
What does semi-definite mean?
Yeah, why it is always positive semi-definite.
I'm asking what's the definition of that term?
Semi-definite?
Yeah.
Oh, it just comes from our definition here. It's just saying, okay, if you use this matrix M, right, satisfy the condition that for every non-zero vector Z, Z transpose MZ is non-negative.
Oh, okay.
This is definition.
Yeah, sorry, I must have missed that slide.
Yeah, that's fine. That's fine. I mean, this is just a fundamental concept, right? So I assume everybody have heard that before, right? Okay, so to show that the grand matrix is positive semi-definite is really is actually quite straightforward. It might be your homework assignment of your linear algebra course, right? So here I just give very sketch or very a brief description. You can verify later, right? So if you write down your n vectors by a matrix, right? Say like n by d, right? So that means each row is just one vector, right? But here I place it as a row vector. Right? So it will be n by d matrix, right? So we can write down the grand matrix essentially is x transpose. Okay? So I would just encourage you to verify that later, right? After class, right? And then it's very easy to show according to the definition. Like any non-zero vector z x transpose z is non-negative. Why? Because this part and this part is the same, right? It's just a vector transpose in a product with itself. So grand matrix is always positive semi-definite. So now, oh, by the way, any questions so far? Okay, great. So how do we associate with some candidate kernel function? Right? So you can imagine if your function k is a valid kernel, right? It must correspond to some speech mapping phi here, right? So if we do the feature mapping, right, and then calculate the grand matrix, we know that each element will be the inner product of the mapped feature vectors, right? Phi xi transpose phi xg. So if your k function is valid kernel, that means your k xi xj will be the same as this explicit feature mapping and dot product. Right? So if we use k function to calculate the square matrix, then the square matrix must be always positive semi-definite as well. But if we use k to calculate such a matrix, we shouldn't call it grand matrix. We call it kernel matrix. Why? Because right now we have yet showing that k is a valid kernel. Right? If the k is a valid kernel, oh, when we calculate it's a valid grand matrix, that's for sure, because we know that k corresponds to some phi. Right? But now that we do not know that, we just want to check that. So we use k to calculate such a matrix. We call it kernel matrix. And then if we can show that for any finite set of vectors, right, we calculate this kernel matrix, you show that it is always semi-positive definite, then we can conclude this k is a valid kernel, namely it corresponds to some informatic. That's the idea. Any question? Someone asked, okay, how do you show that, right? So, well, if you want to mathematically show that, it needs some steps. Right? That's not our focus. We're not gonna cover details, right? But here, I just want to deliver the intuition. I want to check if this particular function is a valid kernel, and now I just use this k and an arbitrary set of input vectors to compute an n by n matrix, right? Every element is a kernel function. It's not kernel function. It's k of these corresponding two vectors. And if this matrix is showing to be positive semi-definite always, then we claim that k is a valid kernel, and the matrix computed based on k is a grand matrix.
So for a kernel which is not consistent according to this definition, which produces a kernel matrix which is not semi-definite, then it's not a gram matrix.
It's not a ground matrix, and K itself is not valid.
Okay. But every gram matrix that is created is a positive semi-definite matrix.
Yeah, it is always positive semi-definite because of its construction. So we want to check that, okay, if every matrix computed by K is kind of like some ground matrix.
So do we use a smaller set of input vectors, or do we use the whole set to create that kernel matrix?
You need to ensure that for arbitrary n, as long as n is finite, like n from 1, 2, 4, 5, 3, like 10,000, 1 million, you need to show for arbitrary choice of n, the kernel matrix you computed is always semi-positive definite. Then you can show, okay, your K is valid, and the kernel matrix is a ground matrix.
Okay.
Any other question? Okay, now let us look at some formal way to check the validity of the function, a validity of kernel function. Right? So this is called the Mercer's condition or Mercer's theorem. So let K x of z to be arbitrary function that maps two n-dimensional vectors to a real number. Right? So it's arbitrary bivariate function where two inputs are of the same dimension, right? Same dimension, right? So K is a valid kernel if for every finite set x1, x2 to xn, right? And can be arbitrary large, right? And for any choice of real value C1, C2, right? We have this double summation to be non-negative, right? So if you write it down, if you write it as matrix vector form, this is essentially saying C transpose K, C non-negative, right? So K is a kernel matrix. So this is the definition of the positive semi-definite. And C here consists of all the coefficients, C1, C2 here. Any question?
Yeah, so for the C values there, right, we're saying Ci multiplied by Cj multiplied by the result of the kernel function, right?
Yes.
Okay. And what did the C and J represent again? Or sorry, what are the C and the two C's, the I and J, Ci and Cj?
Oh, C, I see. So suppose you choose n vectors, right? So you got arbitrary values for the n coefficients C1 to Cn. This is just saying, okay, if you do the double summation from 1 to n, j from 1 to n, you just enumerate every pair of the values of in C, and then multiply with the k function value of corresponding vectors. Their total summation is non-negative.
Yeah, I see that we're doing like every combination of each,
Yes.
Every pair of C's, right?
Yeah.
But like, I guess I don't quite understand why we're doing that.
Oh, this is the same formulation. I mean, the result the same as you write this double summation as this quadratic form.
C transpose and then times K and then times what? There's a second C there
What?
for that equation at the bottom, right? It says C transpose K C.
Yes.
Right. Okay. And so those are the two C's that we have.
Yeah. This C is a vector, so C is a vector concatenating all the C values here. So perhaps I should add a error bar here to emphasize this is a vector.
Ah. Okay.
Yeah. This is a if you write out any quadratic form, right? So like Z transpose MZ, it's just if you expand it, it is this double summation term. Okay. I, ZG, and I'm IG.
Gotcha. Okay. And then you said it's the PSD.
Positive semi-definite.
Okay, gotcha.
Sorry, you will see such kind of aberration everywhere. It just means positive semi-definite.
I get you. I think it was just hard to hear you when you wrote it down, so I was like, what
Okay.
is Okay, thank you.
Oh, when I write down, probably it might affect the volume. So if you didn't hear very clearly, just let me know. Okay.
Sure thing.
Okay. So
Would a linear combination of x actually satisfy that equation?
what?
If we select C as a linear combination of input vectors x1 to xn, wouldn't that satisfy the condition of positive semi-definite, like C transpose KC would be greater than 0?
Yeah, it requires that for every possible choices of x1, x2, all the input vectors, any choice of this C values, you need to ensure that your quadratic form regarding the kernel matrix to be non-negative. When you satisfy this, you can say, okay, K is a valid kernel.
So is it any choice of C, or can it be only one that satisfy?
Any choice. You say every in any. It doesn't mean like if you only pick up one setting of x1, x2, cxn, any set and one setting of c1, c2 to cn, this satisfy, then you can claim. It's not like that. You must ensure that for every possible choices of those x and those c's, and this inequality always holds. Then you can claim K is valid.
Okay.
This is a pretty strong requirement. Any other question? Okay, so now let us look at some commonly used examples about kernels, right? So the first one is called linear kernel. So you can see the definition of linear kernel is just inner product between x and z. So actually there's no feature mapping, right? Or your feature mapping is just yourself. It's the simplest kernel, right? And then polynomial kernel of degree d, which you're gonna calculate the inner product between x and z and take the power of d. But here you actually consider only these orders instructions, right? So someone asks, okay, I want to consider zeros order terms, one order term, two order term, until d order terms. What can we do that? We just add a constant c to this inner product, and then take power of d, and then we'll see that if we expand this term, we'll see that actually by multiplying c with different combinations of the terms, you actually can get all interactions of order d or lower. And here I want to introduce this special kernel, which is very widely used. It's called Gaussian kernel. So how do we calculate Gaussian kernel function? It's very similar to a Gaussian distribution. That's why it's called Gaussian kernel. So we're going to first calculate the squared Euclidean distance between x and z. So subtract x and z and take square now. It's a squared Euclidean distance, right? Then you divide by a positive number c, take minus sign, and take exponential. So we can see that if you choose c to be very small, right, then your kernel matrix will be close to an identity matrix. Why? Because if you write down, right, a kernel matrix, the diagonal element will be kx1, x1, kx2, x2, right? Until kxn, xn, right? So we know that the numerator will always be 0, right? In the diagonal elements. and then your exp to the power of 0 is always 1, right? But for off-diagonal elements, say k, x1, x2, right? So you have a small difference here, so the numerator is non-zero, right? But when c is close to 0, you can imagine some number over some number close to 0, it approaches to like almost infinity. Then you take exponential to minus something close to infinity, you end up with 0, right? That's why. Then we can see that all diagonal elements is almost approximate to 0, right? That's why we say very small c, the kernel matrix is close to identity matrix. But of course, if you have very large c, you have almost 1 everywhere. So the kernel matrix is close to some unit matrix, and I will leave you as an exercise to justify. So Gaussian kernel is a knowing valid kernel. That means it corresponds to some feature mapping, right? So in other words, there exists some feature mapping phi such that the result of Gaussian kernel is equal to phi x transpose z. Right? Then it's natural, right? And I'm curious to know, right? What does this phi? Like, what can we extract this phi? Right? The answer is yes, we can indeed write out this phi. But this phi is infinite dimensional. In other words, if you explicitly spell write down this phi, right, it's infinite dimensional. Right? And in practice, you will never be able to construct this infinite dimensional vector and calculate inner product. You can only go back to calculate the Gaussian kernel itself. So I will leave it as an exercise, right? So it should be the some bonus question. First, can you show that this is a valid kernel? Second, can you write down the feature mapping phi? Okay, any questions so far? So everyone is good? Everyone is comfortable? Okay, great. So someone asked, okay, as we just discussed, right? You might think, okay, maybe kernel function, a valid kernel function, may only cover a small portion of feature mapping, right? Is that enough? In other words, we cannot guarantee every possible feature mapping will find a corresponding kernel function, which we can significantly dramatically reduce computation cost, right? And in practice, actually, we always seek the help of the kernel function. And then people may ask, right, is only the polynomial linear kernel or the Gaussian kernel enough? The answer is no, right? We're always trying to construct more complex kernels to fulfill implicitly more powerful feature mapping, right? How can we construct new kernels, right? Obviously, we can construct from scratch, but there are also other ways, right? Much more convenient. That is, we can construct new kernels based on existing kernels. So there are a set of rules. What you can do is you need to just assemble different kernels. By following those rules, you can construct more and more complex or expressive kernels. So let us just briefly look at those rules, right? So you can multiply any kernel by a positive constant c, you end up with a valid kernel. you can multiply a kernel with a function f, arbitrary function f, on both inputs, right? So f of x times px x prime times fx prime is a valid kernel. And you can plug in the kernel function into a polynomial, the result is still valid kernel. You can take exponential over kernel, it's still a kernel, right? So you can add up two kernels together, you can have a valid kernel. You can multiply two kernels together, you can have a valid kernel. So you can even first perform some feature mapping over x and x prime. Of course, it might be some finite feature mapping, like the computation convenience, and then feed them to another kernel. And the result is still a valid kernel. And also, you can use some symmetric positive semi-definite matrix to construct this kernel, which is called this is called multilinear. So you can see that we have a lot of rules to combine existing kernels to generate new kernels, right? So actually, in practice, we do not worry too much about the expressiveness of your kernel functions, because you can always construct new ones, right? And these new ones might correspond to some enough complex, enough expressive, nonlinear feature mapping. Okay, those are everything we need to know about the kernels, kernel properties, kernels, and kernel tricks. So any questions so far? Great. So now we finally arrive at the exciting step, right? So we talk about many times, like we can extend spot machines to nonlinear case and to be very powerful, all kind of stuff, right? So all the previous discussions are used to prepare for this step, right? How can we combine the dual form of spot machines and kernel trick to easily extend SVM to nonlinear classification case, right? So it's actually really, really easy, right? So everything we have discussed, right? So remember, this is our dual objective function, right? After some algebraic derivations, right? And then we know that, okay, in our original space, in our dual form, we need to calculate the inner product between every pair of the training inputs, right? Now, in the mapped feature space, we just replace the inner product by the inner product after feature mapping, right? And then we apply the kernel trick. We replace this with some valid kernel function. The benefit is in the computation, right? We do not need to explicitly perform feature mapping and do the dot product. Instead, we just calculate feature. We just calculate the kernel function in the original feature space, but the optimization itself doesn't change at all, right? Because we only optimize alpha I, alpha J's, right? Those are just coefficients in our quadratic objective functions. And then again, we can apply any mature, efficient quadratic optimization package to solve that problem. It's pretty standard. And then during the prediction, as we derived before, right? So when we substitute the representation of W for W itself, right? So it becomes a summation over the support vectors, right? Of course, the original derivation is that, okay, it is the inner product after the feature mapping, right? Feature mapping of the support vector and the test input, right? Now we just replace this explicit feature mapping plus dot product by a kernel function. To see that the computation is much easier and does not need to, and it's pretty straightforward. But remember, doing this, right, and also your train your support vector machines with this objective implies that your linear classifier hyperplane stays in a mapped feature space. Even your mapped feature vector is infinite dimensional. That just means in the infinite dimensional space, you have a hyperplane which will separate positive examples, negative examples. And your support vectors stay on or inside the margin, which in the high dimensional mapped feature space as well. Of course, we can all view them in the mapped feature space, right? So we have to project them back to the original feature space. In the projected feature space, original feature space, the margin and the clustering boundary, they are all nonlinear. So now let us look at some result to just visualize that, right? To give us a concrete intuition, right? So here is a nonlinear SVM example based on the Gaussian kernel. Remember, Gaussian kernel corresponds to an infinite nonlinear feature mapping, right? So those are the positive and negative examples. We can consider the blue dots as negative examples and red dots as positive examples. Whatever, it doesn't matter, right? So those circles, right? Circle, I'm gonna use this part, right? Those circle dots are the support vectors. Of course, we look at them in the original input space rather than in the infinite dimensional space where the Gaussian kernel corresponds to, right? In an infinite dimensional space, separating hyperplane will be a real hyperplane, right? It's a hyperplane. It's not some curve or banded planes, right? And also the margin will be some hyperplane as well, right? But here, when we look at them at the original feature space, this is the classification boundary now becomes nonlinear. Why? Because if you write down the classification boundary, which is simply W transpose Bx plus B equals to 0, right? This is classification boundary, right? And in the original feature space, that means you can view it as a function of x. This is essentially a nonlinear function. It is represented by a nonlinear curve. And similarly, if you look at the location of the support vectors in the original space, of course, they will be on the nonlinear margin. Any questions so far?
Yeah, so just one thing, kind of big picture. So you're saying that SVM can handle these like nonlinear mapping, but like if we go back to like the perceptron algorithm, that it can't, like we can't do this same mapping. Like this is one of the big benefits of using this approach. Is that right?
Straight speaking, no. Actually,
Okay.
we can extend perception to kernel perception as well.
Okay.
Yeah, that's a bonus question actually. If you have started the homework before, you will see that.
Okay.
Yeah, you can try to apply the kernel trick in the perception algorithm as well.
So then I guess what's the big advantage then, I guess, of using like nonlinear SVM then?
The big advantage still stays from the theoretical guarantee.
Oh yeah, okay, because we go all the way back to
agnostic learning, the generalization error bound. So what are we doing here? All the way along until now, right? We're still trying to maximize margin while reducing the training error, so that we can tighten the generalization error.
Right. Okay.
But for perception, it doesn't has any regularizer to penalize, complex hypothesis space.
Right. So it's just a more sophisticated version of the perceptron.
Yeah.
Okay.
Okay.
No, that sounds good. Thanks.
Yeah. Any other question in regard in understanding those tricks and ideas and intuitions? Okay, great. So we spent quite a lot of time to discuss about support vector machines. So because this is so important, I'm not saying like um, maybe you guys are like I kind of like hear everything right now, everything about machine learning, about artificial intelligence, about deep neural nets, right? And during deep neural nets can expect some intelligence, whatever, some things, right? But this is not what I start to learn machine learning or artificial intelligence. And that way, support vector machines are dominant. So there's no guarantee that in the next 10 years what will happen, right? So, but the idea, the key idea of support vector machines reflect really, really fundamental. Right? It is based upon theoretical guarantees, and it gives a very elegant optimization structures, and the results reflect many, many concepts. So there are like numerous extensions, variants of support vector machines, and also its applications to a variety of problems. Right? So even nowadays, like people or researchers in my area might, advocate neural nets everywhere. I always advocate neural nets, but they also admit that in many, many applications, SVM will be the first choice. Why? Because it is guaranteed. It is much less sensitive to the number of training examples. So if you run neural nets, it really means that you have to prepare a lot of training examples. You have a lot of GPUs and other computational facilities, right? But for support vector machines, just perform some convex optimization problem and performs really good. It's not always best, but it's always pretty good. Okay, to summarize, like dual form of SVM leads to the concept of support vectors. So if you ask people, ask him, if he said, okay, he knows SVM, and then ask him what is dual form SVM. If he doesn't know that, you can see that you're a liar. You don't know SVM at all. You really need to know the dual form of SVM. And by using the solution from dual form, we can find an interesting structure about the weight vector, right? That is when we make the final prediction, we're essentially computing the dot products. And also this dual form solution structure allow us to plug in the kernel trick into the SVM classifier to easily extend to nonlinear cases. Right? But finally, the kernel trick is not only applicable to SVM. You can apply it to many other methods as well. That's why I mentioned that it is also possible to apply kernel trick in perceptron. If you're interested in that, think about that and try that. Any questions so far? Okay, great. So in the remaining a few minutes, I want to briefly talk about cross-validation. Right? And what is cross-validation? Cross-validation is a way to select hyperparameters. Right? Remember when we talk about perceptron, when we talk about boosting, when we talk about support vector machines, we have some hyperparameters. Like for perceptron, we need to know how many epochs, right? Boosting, how many rounds of learning, how many base learners we want to construct. And for support vector machines, we know, okay, we have a trade-off between, this regularizer and the hinge loss, right? So hinge loss, I'm going hinge loss, right? And as I said, right, we must select it by our hand beforehand, right? before we run our stochastic self-gradient descent or quadratic solver. Right? Then the problem is that how do we select C, right, more reliably? And a commonly used approach is cross-validation. How to? Right? So first, I want everybody to think about, right? So why not we just optimize the hyperparameter like the other parameters, like W and B, right? So we take the objective of the support vector machine as an example. Right? For simplicity, I just use the the primal form, where the objective is the regularizer times the hinge loss max y minus the function margin, right? Why not we just optimize C in this objective as well, like similar as WB? What is the problem?
Overfitting.
Overfitting? But let us just put aside overfitting. What other problems do you think might appear? Yeah, we can take a look, right? So here we want to minimize this objective function. So if we want to minimize this objective function with respect to C as well, right? What's the optimal value of C?
0, right?
Yeah, 0, right? Why? Because this hinge loss is always non-negative, right? If you really minimize this objective with respect to C as well, you have no choice. You have to set C to be 0, right? So we see the consequence, right? If we jointly optimize the hyperparameter, right? In SVM, you're gonna lose your hinge loss, meaning that you're gonna you don't need to fit the train data at all, right? That's obviously absurd, right? We cannot do that. In other cases, like in like number of epochs and number of the base learners in boosting, you even cannot find them in your objective function. You even don't have a way to optimize the objective function with respect to hyperparameters. Then how can we select C? Right? So here we're going to talk about this common used methods called k-fold cross-validation. Right? The idea is like that. Like I'm gonna first choose a range for C, right? From which we believe we can pick up a best value. Right? So I may choose 0.1, 0.2, 0.5, 1, 2, blah, 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 right? Whatever. This is defined by yourself. And then we're gonna evaluate the performance of using each particular choice of C. And then we pick up the one who has the best performance. Then the remaining question is, how do we evaluate a particular setting of C? We're going to perform the cross-validation. So we first split the data into k equal sized parts. Right? So k is usually chosen as 5 or 10. Like here, we just use 5, right? So that means, okay, I randomly partition this data into 5 equally sized parts, right? Every time I use one part as the test set, I use the remaining parts for training. And then I test on this test set and get my accuracy, right? So in the first time, I use the part 1 to 4 for training, and use part 5 for test. I get accuracy on part 5. And then I use part 4 for test and use remaining for training. I get accuracy 4, right? And you continue until you enumerate every part as the test and remaining as the training. You get 5 accuracies, right? And then you average these 5 accuracies as the final performance measurement for this particular value of C 0.1, right? So now you get a performance evaluation for one setting of C. Now remember, we have a bunch of candidate choice of C, right? So we're gonna perform the same procedure for every choice of C. See, for example, if finally our performance for 0.1, you get average 5-fold accuracy is 0.8. For 0.2, you got 0.7, blah, blah, blah. And for C equals to 0.8, you get 0.3. No, that's too absurd, right? 0.6, 0.9, you might get 0.55, right? So now you find that, okay, 0.8 is the largest. So you pick the corresponding C value as your final choice. And then you retrain your data. You retrain a model on a full data set with this particular choice of the C. That's the cross-validation. Any questions so far? So is straightforward to everybody? Okay, so yeah, let me just repeat this again, right, to reinforce, right? So at the beginning, we split the data into k equal size parts, right, randomly split. And then for each particular setting or particular hyperparameter choice, we're going to train a classifier on k-1 parts and then evaluate on the remaining one. We repeat this using each of these k parts as the validation set, right? You get a performance accuracy on each validation set, and then you average these k estimates of the performance as the quality of this hyperparameter. Okay? You get one performance measure for this one setting, right? And now you just repeat for every hyperparameter choice. You get the performance measure for every choice, and finally compare with them and pick up the hyperparameter choice who has the largest performance, namely the k-fold cross-validation accuracy. And then you retrain on the whole data set. You train the model on the whole data set with the best choice of hyperparameter. Yeah, that's it. You train on the full data using set. Okay, great. So let's stop here. I'm sorry for a little bit late today, but we're very excited that we have finished up the support vector machines and also introduced the K-idea cross validation because it's used everywhere in machine learning practice. So in the next lecture, we're gonna start our last topic. It's not last topic, but it is the last most important topic is about artificial neural nets. Okay, see you on next Tuesday.
I have a question about the course in general, if you could.
Yeah, sure.
Yeah, do we have an assignment after assignment 4, or is it straight to the final exam after that?
No, we have one final exam, one final assignment.
Okay, so a 5th assignment and the exam and the final project, or the
Yep.
semester-long project?
Yes.
All right.
Yeah.
Thanks.
So the last the first assignment is actually the second last. Right? Last assignment is mostly about neural nets.
Mm.
Yeah, everybody will be asked to implement the backpropagation algorithm in the neural net and test it on some real data set as well.
Gotcha. Okay, and then for the projects, right, the semester-long project, I will be making a final report on that at some point. When will that be?
Oh, I'm sorry, I haven't released the due, but it will be. I haven't made a decision, but my preferences will be either before the final exam or after the final exam. Perhaps I will choose to be after the final exam, or like several days, to give everybody enough time.
That'd be really good, yeah, because like there's only a few weeks left in the semester, right? So like the least amount of overlap you can give between like the final project and like the semester project, the homework, and the exam. That would be really great. Just try to spread them out as much as possible.
Okay. Yeah, I would definitely consider for that. And the final exam is on May 3rd, and our last lecture will be like, if I'm not wrong, it should be April 27th. So you should have like at least 1 week for the review, and then I plan to give like 1 week more for the final exam. So I think for the final project report, I think that should be enough.
All right, sounds good. Thank
Okay.
you.
Yeah, no problem.